If the state is exactly the same, then they're called bosons. So bosons satisfy the property that the wave function or the state vector, when you interchange any two of them, stays the same. Fermions are the case with a minus sign. Okay, so when you switch two fermions, identical fermions, the state vector changes sign, keeping in mind that the change of sign is itself not observable. It's not an observable thing because the probability distributions, expectation values, everything of interest involves psi times psi star. Fine, so if the state vectors change in this way, then the same must be true of the wave functions. For example, let's take x1, x2 psi. That's by definition psi of x1 and x2. Oops. Wave function of particle 1 and particle 2. On the other hand, x2, x1. That's equal to psi of x2, x1. In other words, the two wave functions are related to each other just by switching the arguments. But now, if the state vectors themselves have this property that they either change sign or don't change sign, then the wave functions must have the same property. So this becomes a property of wave functions. And let's write it down. If you have a wave function for fermions, a system of fermions, x1, and now let's just do it for two particles, and then I'll tell you what to do for many particles. The rule is, for fermions, it must be equal to minus what you would get if you interchange the particles. If you interchange the particles, the wave function changes sign for fermions. What about bosons? For bosons, no change of sign. Plus. Okay, let's think about some states and see what. Supposing let's take the case of bosons first. The case of bosons is a little simpler. No change of sign. Let's suppose we have two bosons in two different states. Well, one state could be, again, forgetting spin. One state could correspond to some particular wave. It doesn't have to be an atom, incidentally. It could just be any system. But let's take some of these atomic states here. Okay. This wave function, or the wave function associated with this state here, could be called psi 0, let's call it. 0 because it has zero angular momentum and because it's the lowest energy state. Alright, so we're going to put particle 1 into that state. So the wave function for particle 1 would be psi 0 of x1. Let's put the next particle in some other state. It could have the same angular momentum or a different angular momentum, but let's make it a different state. Well, let's first do the case where we put the particles into the same state. Oh, let's put two particles into the same state. Then the state vector would be psi 0 of x2. Particle 1 in the state psi 0, particle 2 in the state psi 0. Does this satisfy the rule for fermions? Does it satisfy the rule for bosons? Well, this structure here is obviously unchanged if you interchange 1 and 2. It doesn't matter which order you multiply wave functions. Wave functions are just have numerical values. They're not operators, they commute. Okay, so this wave function here, 2 particles in the same state, that's symmetric. The word is symmetric. Symmetric under interchange of the 2 arguments of the wave function. It does not change sign. So if such a wave function makes any sense, it makes sense only for bosons. For fermions, this is not possible because this does not satisfy the rule for fermions. Okay, let's try another state. And another way of saying it is you can only put bosons into the same state. 2 bosons into the same state. Okay, let's take 1 particle and put it into psi 0, and the other particle put it into another state which I'll call psi 1. Okay. What happens if I interchange 1 and 2? Not 0 and 1, but what happens if I interchange x1 and x2? This will become psi 0 of x2, psi 1 of x1. In general, if these are 2 different wave functions, the left side and the right side will neither be equal to each other nor equal to their negative. Just product of 2 functions. Sine of x1 times hyperbolic mousse of x2. That has no symmetry whatever. It doesn't change sign or it doesn't stay the same. So this is not a possible wave function for either fermions or bosons. Does that mean you can't put 1 particle into 1 state and another particle into another state? Not quite. Let me now take a state which is made by taking both of these combinations here and adding them. This is a wave function, perfectly good wave function. It's a superposition of particle 1 being in psi 0, particle 2 being in psi 1, and the opposite, particle 2 being in psi, but both of them have a particle in psi 0 and a particle in psi 1. They both satisfy the criteria that there's a particle in psi 1 and a particle in psi 2. So both states have been filled. But what about this? What happens to this if I interchange 1 and 2? Nothing. It stays the same. Okay? So this is a perfectly good candidate for a boson system. 2 particles in the same... No. A particle state 1, in state 0, and a particle state 1. And here's how you build it. What about fermions? Can you create a state with a fermion in this state and this state? Yes. All you have to do is put a minus sign. Okay. Can you check? Does that change sign when you interchange x1 and x2? Sure it does. This one goes over to here. This one goes over to here. The whole thing just changes sign. So yes, you can put, in both cases, you can put a particle into state 1 and a particle into state 0. What you can't do for fermions is put 2 particles in the same state and 2 particles, or for bosons you can. Okay. In particular, let's take the special case of exactly this, where psi 1 and psi 0 are the same state. It's just a special case in which, instead of taking 2 different states, I take the same state. Okay, so 2 possibilities, psi 0 of x1, psi 1 of x2, plus psi 0